Hello again, class. We are going to continue our lectures on Chapter 2, Limits and the Derivatives, sections 1 through 3, really focused on limits. We were introduced to the definition of derivatives in section 4, and we found the definition of a derivative, and we used that definition to find f prime of x for different functions. Now we're going to look at some patterns that happen, and it's going to really allow us to talk about the differentiation properties. So here are our objectives for this section. We're going to talk about the power rule and the differentiation properties for derivatives. So here are different types of derivative notation. We know that y is equal to f of x, right? And so the derivative of f at x may be represented by any of the following. F prime of x, that's how you say this one. F prime of x, where this little guy is called prime, and this is y prime. Notice that little guy is called prime, y prime, and this is dy dx, okay? So let's take a look at the slope of a constant function. What is the slope of a constant function? It's just a horizontal line with a slope of 0, so you would expect that f prime of x is equal to 0. So this particular example leads us to theorem number 1. If y is equal to f of x, y is equal to f of x, and f of x is c, which is a constant function, just some value. For example, y equals 3, y equals 300. Then y prime is equal to f prime of x, which is equal to 0. And basically, the derivative of any constant function is equal to 0, and that is our first theorem. The power rule. This theorem is very important. Notice in big, bold, red, capital letters, and it will be used a lot. I mean, you really use this particular theorem a lot. So we're going to call f of x to the n. It's any kind of power function, x to the 1/2, x squared, x to the 5/2, x to the 7th power. This is a power function. It's where n is greater than 1, and radical functions being n is greater than 0 and less than 1. Okay, so what is the power rule? If y is equal to x of n, right, then y prime is equal to f prime of x, which is equal to dy dx. Okay, notice we used all three values, or all three definitions of a derivative. Notice what they do. If f of x is equal to x to the n, they take that n and they bring it down, and that's this guy right here. And then the new exponent is n minus 1. We'll look at some examples of that in a little bit. So let's use theorem number 2 for example number 2. Here we have f of x is equal f of x is equal to x to the 5th. Okay, and so the power rule right here says that if x, the derivative of x to the n is, you bring that n down, and right here, and you do x to the n minus 1. So in this case, n is equal to 5, and so you plug in that value for n in this little guy right here, and we are left with 5x to the 4th power. They brought the 5 down, and then here is 5 minus 1, which is 4, and that gives us our new exponent. Another example, so f of x is equal to the cubed root. That's how you read that. This is the cubed root of x. So you can actually rewrite this another way, and you can see here that they write f of x is equal to 1/3. And so if you remember, if we have a x to the m over n, right, and that is equal to x to the m over n, and so inside here it's x to the first power, so this becomes x to the 1/3, which is how they got this guy down here. So we take the derivative again, in this case n is equal to 1/3, and so we have 1/3 is equal to x to the 1/3 minus 1, and that gives us our new f prime of x here, which is 1/3 in the beginning, and 1/3 minus 1 gives us -2/3, and you want to rewrite that here as get rid of that negative exponent, and now you have 1/3 the cubed root of x squared, and that's how you read this. This guy right here, this is the cubed root of x squared, okay? So now theorem number 3. Theorem number 1 was the constant function. Theorem number 2 was the power rule. This is called the constant multiple property. So if you have some function f of x, and it is equal to some constant times a function, u of x. K can be a constant times a function. Then we can pull that k out and only take the derivative of u of x. So y prime is equal to f prime of x, which is equal to k times u prime of x. You don't have to try to find the derivative of all the values of k times u. You can just pull that k out and take the derivative of u. What does that look like? Notice here we have f of x is equal to 7x to the 4th. We are actually going to use theorem 3 and theorem 2. Why? Because we have a power rule right here, and then we have a constant right here. And so what is our constant? Our constant k is 7. Our u of x is equal to x to the 4th. And so notice we are going to now do k times u prime of x. All right, and so what is u prime of x? U prime of x is equal to, bring this 4 down, x to the 4 minus 1 is 3. And that's how they get this guy down here. So we're applying the constant multiple rule and the power rule to this problem, and 7 times 4 is 28x cubed. All right, so the sum and difference. Sorry, I'm moving around here. Notice if y is equal to f of x, and this is equal to the sum, which is this plus right here, or the difference, which is the minus, of two functions, right? U of x plus or minus v of x. Then the derivative of those two differentiable functions is also the sum of those derivatives. And what does that mean? Well, we're going to look at that in the next example. And it's also equal to the difference, so the sum and the difference, okay, of two functions. So here we have several things happening. We're going to use theorem 2, 3, and 4 for this particular problem. And it looks hard, but it's really not too bad. Let's take the derivative. Let's at a time. Here is the answer, but we're going to do this one at a time. So let's take a look at 3x to the 5th. Let's bring that over here. This is 3 times 5. We're going to bring that 5 down, right? X to the 5 minus 1 is to the 4th. And notice we have a plus sign, so we're just going to keep adding our derivatives. The derivative of x to the 4th, you bring that 4 down in front, so we have 4x to the 4 minus 1 is 3. And then we have a minus sign, so let's bring that minus sign down. And you're going to bring this 3 down in front of the 2. So 2 times 3 is 6x. 3 minus 1 is 2. Again, another addition sign. We're using the sum and difference rules. So 5, bring this 2 down. 5 times 2 is 10x, because 2 minus 1 is 1. Again, a minus sign here. So 7x, let's take a look at this a little bit more closely. It's really 7x to the first power, right? So you bring that down, and then you're left with 7 times x to the 1 minus 1, which is 7x to the 0 power. Not the 7 goes away, but this x to the 0 power just becomes 1. And so the derivative of 7x is just 7. And if you remember, the derivative of a constant is 0. Okay, so we don't have to add that in. And so here we have 15x to the 4th. Here, 4x cubed minus 6x squared plus 10x minus 7, which is what we found here. Okay, as far as applications are concerned, the rest of the examples happen to cover the tangent line and the marginal cost. We did a tangent line problem in section 2.4, and we're going to spend a lot of time on the marginal cost and revenue costs in section 2.7. There's no instantaneous velocity problems, so I'm going to skip through the next few examples and go to the end of the section. Okay, so here are our 4 theorems, and I'm sure we'll run into the velocity problem again. But here are our 4 theorems. The derivative of a constant function is 0. The derivative, this is the power rule. This is the sum and difference rule down here, and this is a constant multiple. All right, those are our 4 basic properties of a derivative. These are the shortcuts as opposed to doing the definition of a derivative every single time we have a problem. These nice mathematicians have figured out there was a little bit of a pattern, and you can use these 4 rules.